Hello again, it's Randy, and we are asked to solve another machine problem. So this time we're going to be solving ordinary differential equations using various methods. By various methods, I mean Euler method, the ODE 45 method that we learned in MATLAB Academy, and then finally solving it symbolically using symbolic math. Okay, so as it says here, develop a simple M file to implement Euler's method for any function of the form dy over dt as a function of y and t, where y is the independent variable and t is the dependent variable. So our code requirements would be format the name of the function must be the Euler method with the form tsol ysol is equal to Euler method dy dt titf h and y naught. Okay, so for our input variables, we have a dy dt is the function of y and t. That is the right-hand side of the differential equation. B, the initial time ti and the final time tf are the initial and final values of the desired range of the independent variable. H is the required step size, and d y naught is the initial value of the dependent variable. So our output variables would be the vector of tsol with the range of the independent variable using the increment h, and ysol is the vector of solution for dependent variables. Okay, so we can work with that. I went ahead and made the .m file that has our function name on it. Okay, so we are going to start coding that. So of course we are going to have function first, and then tsol ysol is equal to the Euler method with its derivative function ti, tf, and the step size, and of course the initial condition. Okay, so we have to define what we need. So what we need for this one is time with the range of the initial time, the step size, and the final time with the n length of time. And then we are going to make a for loop for this one since we are going to be dealing with 1 by n matrices. So let's make a for loop for I equals 1 to n minus 1. And then we have t equals time of I. And then our Euler method equation, which is y equals y naught plus dy dt y naught t times h. And we're going to have y sol of I is equal to y. And then t sol of I is equals to t plus h. Then we equate y naught equal to y. We're going to omit those. And then, of course, end our for loop. And then end the function. So we're going to test that out now by going to part 2 of this machine problem. So we need to write a script to solve the differential equation, the derivative of y with respect to t, which is equal to y times t raised to 3 minus 3 halves multiplied to y over the interval t equals 0 to 2, where our initial condition is 1 using the following: analytically using symbolic math, using the code that you developed in the Euler method function with a step size of 0.5 and 0.25, using the ODE 45 function that was taught in MATLAB. So we need to solve everything in one script. We need to display all our results in one graph and use different color and marker types for each solution except for analytical. So there should be 4 graphs. So on a separate graph, we're going to plot the 2% relative error for 2 and 3. That's this one and this one as compared to 1. And we're going to use the same color and marker type that we used in requirement 2. And of course, we need to properly label the graph. Okay, so we can also work with that. We're going to go ahead and define our variables. So we have our initial time, 0, our final time, 2. I want to omit that. So why not? Our initial condition is 1. And the first given step size to us is h1 equals 0.5, h2 equals 0.25. Okay, so we are going to start using our Euler method function for the first. Okay, so we are first gonna start using our Euler method function first. So since we're gonna be plotting stuff, I'm gonna have a figure handle here, our first figure, figure 1. So we are gonna define our derivative, which is dy dt is equal to at y of t, which makes it a function for y and t, multiplied by t cubed minus 3 halves multiplied by 2y. We're gonna omit that. And then finally, we're going to use our Euler method function. So we have t sol 1, since we have different step sizes. Y sol 1 equal to Euler method, since we're going to be using our Euler method, of course. And then our function, finally, with the range of our initial time, our final time, with the step size of h1, and our initial condition. So next, we are going to do that again. Oh, wait. First, let's test our function first, if it works. We're not going to omit this. Then we're going to run that. Okay. So it looks like it definitely works. It gave us a 1 by n matrix. And then we are going to go ahead and use a step size of 0.25. So t sol and y sol 2. And then h2. We're going to run that. Okay. Good. We're going to omit those. And then finally, we are going to plot them against each other. So since we're going to have two plots, we're going to use our hold on function. And we are going to plot them. With circle markers, with the red color and dash lines. Oh, that should be y sol 1. And we have y sol 2, y sol 2. And let's make this a green triangular dash line. Let's hold that off. And then let's run that. Okay, so there you go. That's our function, but not yet. These are only approximations by the Euler method. So we are gonna go ahead and use the exact analytical solution using symbolic math. So since we're still gonna be using the same graph, we're gonna use hold on, and then of course, since we're gonna be using symbolic math, sims y of t, and then we're gonna define a different equation using a different method. Y times t cubed minus 3 halves multiplied by y. We're gonna omit that, and then our initial condition, y naught is equal to 1. And then we're going to use dsolve for this one. What dsolve does is it essentially does the same as solving the ODE for you using symbolic math with a specific initial condition. So we are going to go ahead and run that. Let's not omit that first. Okay, so that looks pretty correct to me. And then we are gonna go ahead and fplot this equation 1 with a range of our time, so 0 and 2. So let's go ahead and run that. Okay, So apparently this is what our function should look like according to symbolic math. We're pretty close, but since our step sizes aren't small enough, we can't get there just yet. But we gotta remember is that Euler method approximates a function with a certain step size. So the smaller you make your step size, the closer we get to the approximated function. So for example, if we use, let's change this one to 0.1 step size, then we're gonna run that. That's gonna be a green colored triangle. There you go. It's getting closer to our approximated function. And then let's use a smaller number. Let's say 0.01. Let's run that. There you go. It's getting really closer. Okay, so now that we've done that, let's turn that back and then do our next task, which is solving this ODE using the ODE 45 function. Okay, so to use ODE 45, we need to have specific variables. So if we search up ODE 45 here, we can see what we're going to be using, which is this. We need to have a t-span and an initial condition and our ODE function. Of course, it's going to release two certain matrices. Let's go ahead and do that. So we have our t, I want to call it range of ti to tf, and then we're going to omit that. I want to omit this too. And of course, we need to use the ODE 45 function now. So we're gonna have a different t sol and y sol. So let's give this capital T and S and capital Y and S. Oh well. Then we equate it to the function ODE 45. So for this one, we're gonna have to make a function that is in the same script that contains our differential equation, which is this one. So we're gonna go ahead and do that. So we have function dy dt is equal to the, we're gonna name our ODE given ODE as a function of t and y, and then we are gonna define our differential equation itself. So dy dt is equal to y times t raised to 3 minus 3 minus 3 halves multiplied by y. Okay, so since we have defined our given ODE, we're gonna call on it using the at function. So given ODE, and we're gonna have our t range, oopsie, and our initial condition. Okay, since we are gonna have another plot here, we are gonna hold on. Forgot to hold off here. And then finally plot t sol against y sol. And then we're gonna have an x that is color blue. Then we're gonna have dashed lines. So we are gonna run that. Oopsie, we forgot to omit that. That's a lot of values. Okay. Okay, so here you can see that the ODE 45 function is much more accurate, but only because we can't give a step size to it. So it basically approximates exactly what the derivative is, but not really. It's there, but it's not really there. It's really close though. So next, we are gonna hold that off first, and then we're gonna get the 2% relative errors. So next, since the variables don't really match each other's dimensions, we are going to use the substitution method to define a matrix that matches the same matrices as our t sols and y sols. So we have 45 by 1, not t sol, we're going to be using y sol. There you go. We have a 45 by 1. But since we're dealing with a single row and multiple column, we're gonna go ahead and make our YSOL a row vector. We're gonna use that. Let's see first if it works. There you go. We're gonna omit that. Okay, so we needed to omit this. Okay, there you go. Looks much more cleaner now. And then we are gonna solve for our 2% relative error. So as I've said, we need to define a matching matrix for our YSOL values. So we're gonna use, since we're gonna compare it to 1, the analytical method, we're gonna use that. So we are gonna define equation 2, and then we are gonna substitute. So for that, we are gonna use subs our equation 1, and then we're gonna substitute t with linspace, of course, a range 0 to 2, and then the matrix size of our first t-sol, which is, okay, 1 by 4. So we're gonna make this 4. The next, we're gonna have our third equation, 3. We're gonna use subs again. We're gonna use equation 1. We're gonna replace t with linspace 0 to 2, our initial value and final value, and then the size of t-sol 2, or y-sol 2, sorry. So it's up to 8. And then finally, our third equation, subs 1t linspace 0 to 2 until the size of our YSOL, which is 45. So let's see first if we get the correct values. Okay, so we need to double that. Well, not really, but if we want a better looking number, we can double it. Okay, so let's run that. Okay, now we have better looking values. We're gonna go ahead and omit these. Okay, so to get the true percent relative error, oh wait, we made a mistake here. Need to rename that properly. We need to use our 2% relative error formula, which is the actual value. So let's define that first. So the actual value, our equation 2, minus our first YSOL, 1. And then we're gonna divide it by equation 2 also. Then of course, we're gonna multiply it to 100. Let's see if it works first. Okay, it does work. So we're gonna go ahead and copy that and do the same for our other equations. So we're gonna have YSOL 2 here. Of course, we're gonna change this to 3. Also this to 3. Change this to 4. Also to 4. Then we're gonna use our capital YSOL. We're gonna go ahead and run that. Okay, so next we are gonna plot that against our time to make a graph. So we're gonna plot tsol. We're not gonna use the hold on function anymore because we're gonna put this in a different graph. 1 to against tpre1. Let's make it have the same color and marker size as our earlier examples. All right, we're gonna do this 3 times. I'm gonna hold on this point. And then of course we're gonna change our variables. So we're gonna make this tsol2, tpre2, our capital tsol, and tpre3. And of course we're gonna change our markers to the same as earlier. Green triangles, and then blue X's. Let's go ahead and run that first to see if it works. Oh, vector must be the same length. Let's see what's the problem here. Equation 2. Ah, my bad. Let's name this tpre2, tpre3. Okay. Make this an absolute value, so we don't have negative percentages. Okay, so that is our 2% relative error for every values of ysol with respect to time. So let's go ahead and graph these graphs properly. So let's go ahead and give so so let's go ahead and give these graphs a proper label. So let's go ahead and give these graphs a proper label. So let's go ahead and give these graphs proper labels. Okay, so we're gonna have X label our time t, and then Y label our Y, and then let's name it graph of the ODE, put a space there. Ah, Y. And its various approximations. We should also give it a legend, of course. So we're gonna have legend Euler method when h equals 0.5, Euler method when h equals 0.25, and the exact analytical solution, and then our ODE 45 solution, and then we're gonna put it in the best location that MATLAB can think of, best, and then we're gonna limit our graph. So we're gonna give it an X limit, of course the range of t 0 to 2, and a Y limit of 0, and a Y limit of 0 to 3. And then we're gonna graph our and then we're gonna label our second graph Let's go ahead and do that. We're gonna put hold off here. So of course we're gonna use the same X label and Y label. Of course we're gonna change our Y label to the percent error, and then use xlim 0 to 2, and we're gonna give it a title. So percent error compared to the actual value AV at a certain time t. Of course, we're gonna be using the same legends. Let's run that first. Remove this. And there you go. We have our matching graphs with the matching colors and markers. And I think that's about it. I think we have solved this machine problem. Although our code looks really clumpy, we can still fix it. But we're not going to do that now. So thanks for watching, and I'll see you again next time.